Hello everyone, I'm Víctor Gómez, and I'm gonna present a brief my work during my thesis, Improvements in Helicon Plasma Thruster for its evolution towards a space application. This is an industrial PhD made in collaboration with CENER, and the technical work I'm gonna present you was done between 2019 and 2021, so it's a bit older, let's say, but still valid. Who I am? I'm a 10 years experienced aerospace engineer with several steps in the industry. I studied aerospace engineering in the Polytechnic of Madrid, and then I was working for CENER until 2021, and then I moved to the orbit, Clade Space, and now I have founded my own company, Orbital Paradigm. It's not very well fit, sorry. The motivation for the thesis is to exploit the potential use of helicon sources for developing, producing, and commercialize an electric propulsion system for satellites. As such, the industrial motivation will mark each stepping stone in the pathway. For instance, the goals are related to understanding the advantages and limitations of this technology to be applicable for space, to evolve from prototyping to an engineering qualification model, evaluate the thruster performances in order to assess that everything could fit into a space propulsion system, support the system growth based on the research that we are carrying out as part of the thesis, and consolidate and improve the figures of merit of the technology. The methodology that we have followed is based on active prototyping evolution. Basically, we start developing prototypes, testing them, advancing them in the frame of the projects that we have in the background, with continuous evaluation and characterization with direct measurements and indirect measurements. In parallel, we were developing also the subsystems that complementary fit the full system, the fluidics and the power subsystem. So the background is the industrial development that was supported by two programs, a GSTP program, which is called Improvements in Helicon Plasma Thruster for its space evolution towards space application, which is the title of the thesis, and Horizon 2020 consortium program called IPATIA. During those projects, we were focused on the thruster development and also on the full system development, but as part of the thesis and as part of the main core of the projects were the thruster itself. And with that background, we started working on the thesis. The thesis departed from a previous prototype that we developed together, CENER and EP2, which was called HPT05M. That prototype was based on electromagnets. And with that prototype, the first thing I carried out was a full characterization of the envelope of the working envelope of the system, meaning that we were exploring the power that we can supply to the system, the magnetic field that we can use, and the mass flow rates that we can for which we can work with the thruster. With that, we characterized the full electrical response of the system. We did an electrical model of the thruster, and we use it for developing the electronics. This model can be extrapolated to the plasma model of the thruster, but it needs to be reworked because it was very simplistic and oriented fully to the electronics. Then from that, we started advancing the prototypes. The idea was to go from the electromagnet to permanent magnets. So for that, the first step is to get a magnetic field that is representative of the electromagnet in such a way, considering that the physical differences are large. And we get a preliminary first prototype of permanent magnets, which is the one that you can see in the center, that quite well fit, based on indirect measurements, the results that we obtained previously. Due to the schedule of the project, we had to push a little bit faster, and we make an advance without supporting the activity with testing, And we achieved an HPT03 model that it's there in the right, which was compact. It was suited for space, so power levels were well suited for space. The magnet was pretty light, but the performances were very poor. We weren't able even to ignite it properly, and the mass flow ranges that we can explore were very, very, very limited. So we decided to go back one step and go back to experimentation, prototyping, and we developed 2 prototypes based on permanent magnets. Those prototypes were quite flexible. We were able to change the magnetic field, maintaining the topology, which was one of the keys, and we were able to change the different parts on the assembly in order to explore their impact in the design and the performances. With that, we were able to more or less achieve an acceptable level for the project evolution, because the project was pushing us forward and we had to decide and fix our design and perform some further testing for the project that we were developing for the Horizon 2020. So with that, one of those prototypes, we performed the first system integration test, which included the fluidics, the electronics, and one of the thruster models that I have shown you before. This milestone was very important from the project because we were able to demonstrate that the system was able to work as a system itself. We were able to further characterize the thruster response, which was a first initial input for the automatic control that we are gonna include in the thesis. And it was one of the key points for the project to continue ahead. As part of that campaign, we characterized the thruster response with various measurements based on the work that Mick Weinen did for his thesis. And there we found out that the performances of the thruster were very, very poor. Basically, we had very limited thrust, very limited specific impulse, and very low efficiencies. The main point that was a drawback, I think, in this situation was that the project, the industrial project, was pushing too tight the schedule, the way we advanced the prototyping itself, the way we had to submit those models for the European Commission, and we didn't realize that we were doing a bad work, let's say, between brackets. The system integration was well, but the performances were very poor. So here, this doesn't mean that technology is worth it. This means that the prototype is not working. Because from the previous prototypes that we had, the indirect measurements that we had were much better, but we cannot achieve that level of performances. And last but not least, I finished the work on the technical side, implementing the autonomous control for power control, which is focused on providing the maximum power to the thruster. I did a minimization controller here in order to get the minimum reflected power. And and I designed the assembly for the EQM, which was implemented later when I was off of CENER. So it was implemented by the team. What's next? Well, I have pending the publication of a paper in journal. It's pending an internal iteration and resubmission because it was rejected, and the thesis writing. So basically, I'm almost there, but I have to work a lot, as we were mentioning before the presentation. These are the publications and contributions that are quite older. Thank you for your attention. Any questions?